In today's video, I'm going to show you how to solve this dimensional analysis problem. Let's look at the problem. In this problem, we are to check the dimensional correctness of v squared equals u squared plus 2as. So this is an equation that we are going to apply the technique of dimensional analysis to check the correctness of this equation. However, if you look at this equation, we have three terms. We have v squared equals u squared plus 2as as one term. We are also given the definitions for each of these quantities in this problem. So v represents the final velocity, u represents the initial velocity, a represents the acceleration, and s represents the displacement. Let's look at the solution. We are given the equation v squared equals u squared plus 2as, and the task is to use dimensional analysis to check the correctness of this equation. Check the correctness of this equation means that we are to check if the left hand side of the equation has the same dimension as the right hand side of the equation. So this is what we are going to check in this problem. Now, if we say dimensional analysis, we are to express each of these quantities, which are physical quantities, into their base units. In physics, the three basic units we have are: one, mass. So mass is the amount of substance in an object, and it represents one of the dimensions in physics. Now, mass is represented as uppercase M. Again, don't confuse this uppercase M to the unit meters, which is lowercase m. Okay, so one of the base unit is mass, which is defined as the amount of substance in an object, and it has the units, as we know, of kilograms. The second base unit we can talk about is length, and in dimensional analysis we represent that with uppercase L, and it has the unit of meters. You need to be careful with the unit of length to the dimensional representation of mass, which is uppercase M, and the unit for length is lowercase m. And the final base unit that we are interested in is time. And in dimensional analysis, we represent time with uppercase T. Time has the unit of seconds, lowercase s. So here you can clearly see the difference that for mass, which is the amount of substance in an object, in dimensions, we represent it with uppercase M, to length, which is the interval between 2 points. All right. So that interval between 2 points has the dimensions of length. So any distance at all will have the dimensions of length. And in dimensional analysis, we will represent that with L, uppercase L. And finally, we have time, which we can define it as the interval between two events. All right. And in dimensional analysis, we represent it with uppercase T, and it has the unit of what? Seconds. Now, knowing these three basic units, we need to express each of these quantities in this equation in these three base units. So first we have v squared equals, so the v squared is on the left hand side of the equation, all right, and that is equal to u squared plus another term 2as, and each of these terms are defined for us, which is very important in solving dimensional analysis problems. So we have the velocity, which is delta x divided by delta t, that is the change in position with respect to time. In this case, the change in position is the displacement, so it represents just an interval between 2 points. So it is going to have the dimensions of what? Length. Again, we have the initial velocity given as u, which is also velocity. So whether final or initial velocity, it is velocity. Velocity, as we know, is defined as the change in position divided by the change in time. Again, this initial velocity is having some quantity, which is change in position, that is dimensions of length divided by the change in time. And then we have another quantity, which is a, acceleration. Acceleration from first principles is defined as the change in velocity with respect to time. So delta v divided by delta t, and then s, which is defined here as displacement. So let's call that as delta x. So these are the four quantities that we have in this equation. position. Note, we have a constant. We have this 2 here, which is a constant. And in dimensional analysis, constants are dimensionless. So we don't have to worry about constants. So this 2 here, we don't have to worry about 2. Now, let's look at the equation again. So v squared equals u squared plus 2as. So this is the equation we are going to check its dimensions on both the left and the right hand side to see if it is correct or not. So we've already broken down these quantities into their base quantities. That is velocity as change in position with respect to time. U is also velocity, which is also change in position with respect to time. Acceleration is defined as the change in velocity with respect to time. And this S we are told is displacement in this problem. However, in dimensional analysis, we place the quantity in a square bracket. So if we have, let's say, position or displacement, so we place it in a square bracket such that the square bracket is here, and then we place the quantity inside the square bracket. For example, if we have quantity A and we want to take the dimensions of quantity A, then we place it inside a square bracket. So this tells us that the dimensions of quantity A. So we can do that for each of these quantities since we now know the definitions for each of these quantities. So let's look at first one, which is velocity, delta x, change in position with respect to time. So to find the dimensions of velocity, we place it inside a square bracket. That is going to be equal to delta x divided by placing the time inside a square bracket, delta t. So in this case, the dimensions of velocity is going to be L, because displacement is simply some interval between 2 points. So it has the dimensions of length. So we represent it not with the unit, but with the symbol that we use in dimensional analysis for length. So that is L divided by what is the dimensional representation of time, capital T or uppercase T. So using indices, we can express this as LT to the power minus 1. So the dimensions of velocity in this case is LT to the power minus 1. Okay, the initial velocity will follow the same approach. So delta x divided by delta t, because generally that is the definition for velocity. So whether it is initial or final velocity, we just have to express it in the same way. So we have the dimensions of that initial velocity is going to be the dimensions of displacement divided by the dimensions of time. So the dimension of displacement is length divided by the dimension of time, which is also t. So we have again LT to the power minus 1. Again, this tells us that you don't really have to worry if the quantities are the same, because here we see that both the initial and the final velocities have the same dimension because they represent the same quantity. Awesome. Now let's look at acceleration. So we have A, and we define acceleration as change in velocity divided by change in time. So to take the dimensions of acceleration, we place it in a square bracket, and then the dimensions of the velocity, change in velocity, divided by the dimensions of time. So now, if you look previously in the first two cases, we have the dimensions of velocity, which is L over T or LT to the power minus 1. We can directly import that here in the numerator. So we can have LT to the power minus 1. Now again divided by the dimensions of time, which is t. So using the laws of indices, then that is going to be LT to the power minus 2, because this is to the power 1. If we take it up there, it subtracts from this one. So we keep the common t and then add the powers. Now finally we have displacement, S. Displacement is just the change in position. So the dimensions of displacement is going to be delta x. That is simply L, because it's distance or it's interval between 2 points. Therefore, it's simply L. We have all we need to substitute or plug into this equation to check if indeed the left hand side is the same as the right hand side. If that is the case, then the equation is dimensionally correct. If not, then the equation is not dimensionally correct. So let's see. Now we have v squared. So v squared would mean we have LT to the power minus 1, that is v, however that is squared, equals we have u squared, so that would mean again LT to the power minus 1, also squared, plus 2. Again, I mentioned this 2 is a constant, so it is dimensionless. And then we have acceleration, which is LT to the power minus 2. All right, we already found it here, acceleration. And then finally, we have displacement, that is the S. So multiplying L. Now we can apply the laws of indices to simplify this equation so that we can compare the left-hand side and the right-hand side. So LT to the power minus 1. So this square outside this bracket affects both letters, L and T. All right, so we have L squared T to the power minus 2 equals 1 L squared T to the power minus 2 plus 2L squared T to the power minus 2. This will result into L squared T to the power minus 2 equals, so 1 plus 2 because these are like terms. And that is one thing about dimensional analysis. You can always add like terms, just like we do in algebra. You can always add like terms. So quantities of the same dimensions can be added. That is, you can add apples to apples, but you cannot add apples to oranges. So in this case, we have L squared T to the power minus 2, 1 of that plus 2 of that. So that gives us 3L squared T to the power minus 2. Again, remember, we don't worry about constant in dimensional analysis. So we can drop that constant. So we can see that we have on the left-hand side equals the right-hand side, such that L squared T to the power minus 2 on the left-hand side is equal to L squared T to the power minus 2 on the right-hand side. If you want to write it in terms of fractions, then you can do L squared divided by T squared equals L squared over T squared. All right, that means that the equation V squared equals U squared plus 2AS is dimensionally correct because the dimensions of the left-hand side is the same as the dimensions of the right-hand side. All right.